So just wanted to say once again, it's a pleasure to have Dr. Laura Alder joining us from University of Illinois at Urbana to talk about a very interesting project, the GeoCoronal Observatory. So yes, ma'am, all yours.
All right, thank you so much. I'm thrilled to be here. I always take advantage of opportunities to speak like this because this is something that's so near and dear to my heart. And I know so many of you knew Dr. George Carruthers, the namesake of our mission. I'm just thrilled. So thank you very much for the invitation. So this is a relatively new NASA mission. We are within the heliophysics division here. It's a little bit of an outdated slide here, but this is NASA's science fleet. You can see where the circled Carruthers Geocorona Observatory up there by the sun. Within heliophysics, within NASA, this is the domain that studies both solar physics as well as the sun's interaction with planets, all the way down, essentially the plasma interactions, down to you get to the neutral atmosphere. And we fit really well within there. We're a mission of opportunity. The proposal was submitted back in 2018. And we are now, as of what is today, March 8th, we've been operational in science phase now for 8 days. And so we're very new. I do have some images to show you, as you'll see. But the purpose of our mission, George called it the GeoCorona. But the purpose of our mission is to study the outermost layer of Earth's atmosphere. It's known as the exosphere. So maybe some of you already know this. Maybe some of you, it's a blast from your 8th grade physics class or your science class. But the Earth's atmosphere is typically categorized in terms of these layers. Earth's surface gravity holds on to the atmosphere. And 75% of the mass of the atmosphere is within a height of just 13 kilometers. In other words, it's the troposphere. And then more than 99.99% of all the mass is within 100 kilometers, and that's the top of the mesosphere. And that's usually what's considered the boundary between Earth and space. A lot of satellites orbit the low Earth orbit is well inside the thermosphere. A little bit gets up into the exosphere. Boundary between thermosphere and exosphere is around 500 kilometers. And what really distinguishes, not much of a discrete boundary. Dynamically, the way this works is this is where nominally collisions between the neutral atoms in this region are so infrequent that you can consider it to be rather collisionless. And I'll talk more about why that's not a great assumption. But this is the basic, again, 8th grade physics view of it. One thing I want to point out here is that this diagram, this was made by NASA's visualization studio. It is, of course, not at all drawn to scale. On this scale, all of everything below the exosphere would fit into the word troposphere, right? And then the exosphere itself would start there and extend so far beyond this slide. We're talking, if you think of things in terms of the Earth radii, and you can see the Earth circle there, it's at least 30 Earth radii away. So, I'm in the next building over, basically, from where I'm sitting here on campus in my office. Now, one of the reasons I think a lot of the graphics that are published and produced in the Wikipedia and whatnot are so frankly terrible is that there's not a lot known about the exosphere. So I get asked, well, how big is it? And the truth is, we don't know. We don't know whether it's spherical or oval. We don't know what the density is. And it's because it's so far away that opportunities to measure it are extremely rare. And so that is the purpose of our mission, is to study this region. Now, one of the reasons we want to study it is because this is the pathway by which surface water, this is the last step on the path where surface water becomes water vapor. Water vapor is dissociated into its constituent oxygen, hydrogen atoms, and it's the hydrogen atoms that are light enough to reach this layer. And that small fraction of them that have radial velocities that exceed the gravitational escape speed, they're lost to space. They're gone forever. And this is exactly the process. It's called thermal evaporation. It was first identified as a meaningful process on Earth by Jeans, back in 1918. It's very, very well known. But this is exactly the process by which Mars lost its atmosphere. So here's a visualization of what people think Mars looked like its ancient days, covered in ocean. And of course, this is what it looks like today. And so one of the things we want to study is that escape rate at Earth and have it help us inform what makes Earth different from Mars, what makes other planets like Earth. How long can they hang on to their surface water? So that's one of the key questions we want to study. Now, one thing we know about what makes Earth different from Mars is that Earth has an intrinsic magnetic field, and Mars doesn't have much of one. This is, of course, this is the classic dipole field. I think most of you are familiar with this, but really, it's the way that the magnetic field at Earth interacts with the sun. And I know you probably know what I'm about to show next anyway, but I never miss an opportunity to show this movie. This is a video of real data taken of a coronal mass ejection. So the sun is, of course, very dynamic. It's in its highly active solar maximum phase now. And these big blobs of plasma with their magnetic field pinch off. And these are huge compared to the size of the Earth. And they can reconnect with Earth's field lines, and all of that energy gets dumped into the Earth system. This is, of course, gives rise to the aurora at high latitudes, but even you can see the field strengths got compressed. There's the plasma environment around Earth changes incredibly dynamically. And even though it's beautiful, it's a huge concern for both space assets. You know, it can cause satellites to deorbit when the density changes. It changes the frictional drag that they experience. And it can also cause ground currents and power outages on the ground. And so this idea of space weather is really what we're after. You say, well, what does that have to do with the exosphere? And this is the link between these two ideas. It's this process called ion-neutral charge exchange. So the exosphere is made up of these neutral hydrogen atoms that were once surface water. A few of them used to be a methane atom at the surface. But these hydrogen atoms, neutral hydrogen atoms, when they encounter, I said it's mostly collisionless, that's true. Neutral-neutral collisions are exceptionally rare. But when they encounter an ambient ion, the electron can jump from the hydrogen atom to that ion, and it neutralizes the ion, assuming it was singly charged, which most of them are. And the ion can either be, this is interesting, either an H plus or an O plus ion. It's actually maybe it's not a quirk of nature, that the ionization potential energies for oxygen and hydrogen are so similar that the charge exchange reaction rates between the electron on an H atom jumping to an H plus or jumping over to an O plus are almost identical. And that means that they can go forward and backward very easily. But when that happens, you know, ions are much hotter than a neutral H atom that had just evaporated off the top of the atmosphere and entered this region. And so when the charge exchange occurs, now you have oops, I went too far. Now you have a cold ion. And so this is a principal mechanism of dissipating energy, especially after geomagnetic storms. The density of those hydrogen atoms directly governs the recovery rate after these geomagnetic storms hit Earth. Another thing it does is that when you have a change in ion species, such as, you know, you used to have an O plus and a neutral H, now you have a neutral O and an H plus, that induces plasma transport. That can change the ion composition in such a way that plasma will flow up and down field lines. And this is one way of refilling plasma depletions in the magnetosphere that were eroded when the storm hit because of all the dynamics in the magnetosphere. You can replenish them from ionospheric plasma sources through this charge exchange reaction. This reaction rate governs how quickly the Earth can recover in that way as well. But what are you left with? You're left now with a really hot neutral hydrogen atom. And it's more likely to escape Earth's gravity. And so what we're really interested in doing with this mission is measuring the exospheric hydrogen density, its spatial distribution, how does it change over time? And we need to know that information. It's not much is known, as I mentioned, in order to have proper, more accurate space weather forecasting, being able to predict recovery timescales, being able to tell a satellite when it should turn off for a little while because the disturbance is going to be large. And then finally, how do we want to understand how planetary magnetic fields then and this charge exchange reaction with the trapped plasma populations that they can support, how does that affect atmospheric escape on these planetary evolutionary timescales? So these are the goals for the mission. We've, of course, codified, as in NASA language, very specific science objectives. We've got two flavors there. So the first one is that we want to understand what happens during quiet time, because even this is not well known. What governs the structure on both regional and global scales? And we know that there are three processes that essentially give rise to this. There's the thermal evaporation. This is dependent on the temperature of the atmosphere. It's, of course, hotter on the day side, colder on the night side, hotter on dusk, colder on dawn. And so we expect to see asymmetries near the source region, this exobase, we call it, the lowest altitude in the exosphere. And then at really large distances, when the sunlight shines on the exosphere, it can actually impose pressure, right? Every, light carries momentum and pressure. And so that radiation pressure, we're expecting it to have sun-Earth alignment. Now, whether it looks like a cometary tail at large distances or whether it looks more like a cigar is, again, something we don't know. And then the charge exchange with these ions, these are co-rotating in the magnetic equator for the most part. They're trapped plasma populations, but most of them are co-rotating in kind of the middle exosphere region. And it's possible that we'll see toroidal symmetry around the magnetic equator. And I'll talk about what that might look like in our images in just a minute. Now, these are just this is some of the very limited data we have to talk about what does the Earth look like. I'll tell you where the data came from in a second, but you can see the contours of constant density here. It looks like solar radiation pressure is playing a big role. There do appear to be some dawn disk asymmetries, but this is a seasonal average made up of multiple years of data. And so far, this is the best we can do at these radial distances. The next objective is, of course, about storms. And this is a very basic question. We just want to know the nature of the transient variability, and maybe we can figure out where it comes from. There's two competing theories here. One is that the atmosphere actually expands outwards. Heat gets deposited during storms into the lower atmosphere, thermosphere region, and that increased heat causes more atoms to have a larger radial velocity, and they essentially float away, enhanced H escape during those times. But what's interesting is that, again, snapshot, we have a storm average density profile. You can see it over here on the left. We're seeing what we think are density depletions at low altitudes, coincident with density enhancements at high altitudes. And that might have something to do with the fact that the hydrogen, as it's produced through dissociation and it's diffusing upwards, it's molecular diffusion governing its upward flow through the atmosphere. It might be that that's so slow that when you blow off the top of the atmosphere, it takes a while for it to come back. And so what you would observe then is depletions. We don't know what's happening. It could also be that there's charge exchange, local charge exchange. This could be local production and loss of hydrogen atoms. We can't tell the difference with the data we have. The two plots I'm showing, the one here on the left and the one on the previous slide, that's all the data we have. And so what we do have is models. Models indicate that the densities, you can see some of the density changes here in density is what we're looking at on the color scale. 40–60% enhancements when a storm hits over a very short amount of time. Right now, all of the models that are used for our space weather forecasts assume that the exosphere is time invariant because there's no data. All we have is a little bit of a model and a little bit of snapshots in time, essentially, to say that something might be going on. And so the Carruthers mission is really going to revolutionize our understanding of exospheric structure, exospheric dynamics, exospheric physics, and especially how it helps mediate Earth's response to these space weather storms. So this is all the science. This is what we're going to do with the densities we get. The big question is, how do we derive density over something that's so vast? It's a massive scale. I actually tried to build, we launched it, a mass spectrometer. It measures locally. You launch it on a satellite, and essentially it's a bucket. It counts hydrogen atoms But to do that on such a vast scale, we would need such a gigantic constellation of these. It's completely impractical. And so remote sensing is the only way to do it. I suspect a lot of you are familiar with the mechanisms by which light is produced in physical media, after physical sources. In our case, we're looking at the light that exospheric hydrogen atoms give off when they are illuminated by solar photons. The sun is, of course, made of mostly hydrogen, so it gives off a lot of hydrogen-colored light. And we're looking at scattering, resonant scattering, and fluorescence. So in the case of the Carruthers emission, we're looking at the brightest hydrogen emission line there is. It's actually ubiquitous in space. It's produced when the hydrogen atom, this is the energy level diagram here, most of the electron, the only electron, is usually they're in the ground state. You absorb a Lyman-alpha atom that excites it to the n=2 state, and then it just radiatively relaxes back down. And when it does, it re-emits that Lyman-alpha photon. Fluorescence is something I do when I observe hydrogen exosphere from the ground. Is when the atom, again, electrons in its ground state, absorbs a Lyman beta photon, and then it doesn't fall all the way back down to the ground. It falls down with this first, it's called a Balmer-alpha line. This is the red color aurora line, or at least one of them. This one is at 65, 63 angstroms. And so that's visible from the ground, but for ultraviolet light, like the Lyman series, you have to observe that from space, because molecular oxygen readily absorbs the Lyman-alpha photons. So it's the sky is essentially dark to Lyman-alpha. Now, if you could see Lyman-alpha and it wasn't being absorbed, of course, we would need more than sunscreen to survive being outside, but it would be as bright as the moon. I mean, it's incredibly bright feature. Just for comparison, this airglow feature, the Balmer-alpha airglow, we've got these little ground-based cameras. The unit of interest here is Rayleigh's. I don't know how many of you are familiar with that. It's more of an aeronomy term for emissions, but it's a million photons per centimeter squared per second. Balmer light is something like 10 to 4 Rayleighs over the course of the night. It decays down. Lyman-alpha is something like 35 to 50 kilorayleighs. It's just incredibly, incredibly bright. So we have to get into space, and once we do, we make observations of the emission radiance. We're looking for how bright is the line, and we use that then to infer the underlying density distribution, hopefully, of the exospheric hydrogens. And we use a numerical model of the emission. It's quite sophisticated. It needs to account for the fact that a given hydrogen atom can re-emit and then be reabsorbed. You know, it's not just the solar photons. Solar photons are the ultimate source, but the atoms themselves, if they're sufficiently dense, such as in the inner exosphere, they can scatter multiple times before it's observed. And that's a highly nonlinear process. So we have a numerical model. We tell it what we think is the density. We tell it what we think the solar flux is. And then we have a predicted radiance, and we iteratively essentially converge the two to find the density distribution that best fits the data. So the more data we have, the better that retrieval ends up being. And that's really been the bottleneck, as I'll talk about. But the biggest bottleneck for the longest time was having a camera sensitive to ultraviolet photons. And that's where George Carruthers comes in. So I think most of you are familiar with the fact that he invented the camera. It was used by Apollo 16 astronauts. They deployed it on the lunar surface in 1972. Here's a picture of it. It's that famous gold-plated camera. The sister instrument, there's almost always you build two, right? One for ground testing and one you send off into space. The sister instrument is currently on display at the Air and Space Museum in Washington, D.C. I'm sure most of you have seen it. And this one is still on the moon. And so it's really, really exciting. And of course, what they brought back then was the film canister. And then here's a picture of Dr. Carruthers himself holding that film canister that was retrieved. And then here's the photograph of Earth's exosphere. This is the ultraviolet light emitted by Earth that his camera observed from lunar surface. Now there's quite a bit of a shadow here. And that's not something we see in pure Lyman-alpha. His camera was sensitive to more than just Lyman-alpha. It was more of a broad spectrum, far ultraviolet, so it was letting in a lot of oxygen emission in particular. Oxygen emission is excited by the sun shines on the Earth, and it's a very prompt emission, and so you end up seeing a pretty sizable dark shadow. We don't see that nearly as much with Lyman-alpha, so that's a little bit of a difference there. But the synergies here, it wasn't just that we're using an ultraviolet camera, very similar to the one that George Carruthers himself built, but it was also that George Carruthers was a 3-time alum of the University of Illinois. And this is University of Illinois' first NASA spacecraft mission. And so the synergies here were just too much to overlook. Dr. Nikki Fox, who at the time was the heliophysics division director, really championed the cause within NASA to have our mission renamed in his honor. So the original name at our proposal stage, Global Lyman-alpha Imager of the Dynamic Exosphere. I love that acronym. I have to admit, I came up with it myself. I'm just as happy to have us now be called the Carruthers Geocorona Observatory. And so, yeah, we are really building on tall shoulders here. So as far as Lyman-alpha observing, I mentioned there have been some observations made. There's really 3 types of observations that have been made. One would be, and this is from space, but the one here on the left, zenith viewing, this is what's done from the ground typically with that Balmer alpha visible line, that really faint one. You essentially put your sensor on the ground and you look straight up. This sensor was actually studying Jupiter. So this is a Japanese space agency sensor studying Jupiter. And so they were in low Earth orbit. It's got a 90-minute orbital periodicity. And every time they came around and looked at Jupiter, they would acquire a measurement. Their line of sight, their signal had contributions from exospheric emission in it. And you know, what was their background and their garbage that they had to get rid of turned out to be really valuable signal for the exospheric community. The problem is that it's only a single line of sight. You're essentially getting a scalar number as a function of time. There's really no way to turn that into a hydrogen density distribution, even if it's a function of altitude, much less spatially around the planet. And then you've got no hope of distinguishing spatial and temporal variability. That being said, they saw a lot of variability, and it was very strongly correlated, I should say, with geomagnetic activity. So that was the first clue that, in fact, the exosphere responds very sensitively to solar storms, and that at that point had not been something that was known at all. The one altitude profile I showed was from during storms that showed that depletion at low altitudes, enhancement at the other, was from what's known as a limb scanning geometry. So the NASA's timed mission had an ultraviolet, they call it a global ultraviolet imager, but it was really a scanning spectrograph mechanically scanned across Earth's limb so that you could have multiple lines of sight in a pretty small amount of time. One of the problems there was that it had low signal to noise. So you had to average over many days in order to get enough signal to do a retrieval. And then meanwhile, it processed, it would look like this for days at a time would be this orientation. It would only slowly process around the Earth. It took 3 months to go all the way around the Earth. So even if you did see some spatial structure, you wouldn't get your global coverage except over spring, for example. And then you'd get the same kind of coverage again for the summer sector. And so it was really difficult to do a lot of global investigations with that kind of a platform. And then lastly, there was the NASA TWINS mission. Now this one was nice. This was a stereoscopic mission. Each spacecraft, there were 2 spacecraft, and they were on these really high altitude Mania orbits, they're called, 12 Earth radii in distance away. And they would look back at Earth, and they each one had these 2 little single pixel photometers, and they would rock back and forth like a windshield wiper, 40 degrees off nadir. So they never viewed close to Earth at all, very much unlike these other 2 platforms. They avoided that entirely, but what they got was something really special, and it's called common volume sensing. Their lines of sight overlapped. That's an excellent constraint on density models, especially 3D density distributions. And in fact, what it enables is something called tomography. So tomography is a technique used, for example, by MRI machines when you get in and they take the pictures from all sides of your brain, and then they use it to build a 3D picture of your brain, for example. We applied that to the exosphere, and that was how we were able to get the contours essentially of density, and start to pick out some of the features, except again, we've got no information about what's happening either inside this region where there's no line of sight coverage or outside the orbit of these spacecraft. Meanwhile, they only work when they're pointing away from the sun, and they too precess. So for 6 months out of the year, they're pointed the wrong way. We can't get any information at all. So this is the state of the field, essentially, when we submitted our proposal. And we recognized right away that the by far, so something George Carruthers himself recognized, by far, the best way to do exospheric remote sensing is from a vantage really far away, and you take pictures with a camera. We want a 2D image, not a line of sight that you have to mechanically manipulate, a single pixel type approach. We wanted a full image. Now, other than George Carruthers' image himself, you can see that here on the left, there have only ever been 3 images of Earth's exosphere ever acquired. Only 2 were made by a proper camera. So George Carruthers, this is his camera. The one here, I don't know if you can see my cursor. This is a Japanese space agency, Procyon. Their camera was named Leica. That was a camera. This was a small satellite mission, actually. You can see it was 2,348 Earth radii away from Earth. This thing went into deep space. But its primary mission was studying exoplanets. And it took 1 picture of Earth, and that was it. It was not an exospheric mission. So we only get the 1 picture from them. When Galileo flew by Earth, it created a composite. It had a UV spectrometer on board, and it made a composite image of Earth's exosphere. Here's the moon. It doesn't mean that the exosphere is as big as the moon, because there's projection effects as to where the moon is in the scene. But certainly it observed it. Again, it was a one-off. This, in fact, wasn't even published ever. And then finally, there was an image acquired from the joint NASA-ESA mission, SOHO. They had a hydrogen absorption cell. So again, not a camera, but they had an absorption cell, and they were able to build up Earth's exosphere as viewed more or less from the sun. So the vantage of this camera, or of this image, is more or less where our camera will be, which I'll talk about in a second. But the idea here, I'll go ahead and mention it. It says here, Earth-Sun L1 point. So this is the gravitational equilibrium between the Earth and the sun, Lagrange 1 point, roughly 240 Earth radii away, about 4 times farther than lunar orbit. And it's a really nice place to essentially park. You don't need a lot of propulsion to have a stable orbit around that gravitational equilibrium point. So it's really convenient for space-based platforms to sit and stare. So anyway, these are the 4 we have. And I'll just say that, in the first hour that we turned on, Carruthers acquired more than this. And we'll be acquiring essentially this many every hour. And we have been for the past several months now. So the fact is, we were truly an opportunistic mission. I mentioned we're a mission of opportunity. And the opportunity we're seizing is a ride to this L1 Lagrange point. It is pretty unusual to have a rocket that big launch a NASA mission, and we never would have gotten the opportunity if NASA didn't have a flagship mission headed out that way. And that flagship was the IMAP mission. We launched as a ride share on the rocket along with NOAA mission. And so the 3 of us shared the same rocket. And here you can see us. We have a pretty gigantic halo orbit around this L1 point. And then we've got our cameras. You can see there's a red cone coming off of the Carruthers and a purple cone coming off of Carruthers. And the size of our orbit, or size of our field of view, I should say, relative to the lunar orbit, we're slightly smaller than lunar orbit. So we go out to about 47 or so Earth radii, and the moon's at 60. We get the moon in our field of view a lot, as I'll show you. But the name of our instrument, the name of our camera, is the GeoCoronal Imager. It was built by UC Berkeley Space Science Lab. They're also currently doing mission operations, all the commanding of the spacecraft based on the science plan that we give them. We tell them what we want to do, and then they write the commands and send it up. But what it gets us is, because we can essentially park ourselves in this orbit we can stare at Earth nearly continuously. There's another little instrument I'll mention. We had a student collaboration effort. It was a separately funded NASA program to have students build something that gets launched into space. And what they built was a little solar flux monitor. So there's this, I'll show you the picture of it. There's a little camera that sits up on top of ours and looks back towards the sun. It kind of peeks over the solar panels and measures the incident solar flux that's shining on Earth. And then we measure that backscattered, resonantly backscattered glow off of the atmosphere itself. So it's a really nice synergy then between their instrument and ours. So I know this community knows a lot about cameras, so I figured I'd go into a few more details about the camera than I typically do in these talks. The GeoCoronal Imager, essentially it's two cameras in one. They have independent optical paths. I'll show you the layout in a second. But they've got co-aligned bore sights. They have very different fields of view. So we're calling the wide field imager, has an 18-degree field of view. It's got lower spatial resolution because what we're really after is the outer exosphere. And what you're looking at here are actual photographs. These were the first photographs we took. They were released by NASA as our first light images. So here's that wide field imager. And you can see we're getting pretty significant exospheric signal. This is Rayleighs over here on this side. I'm sorry, it's kilorayleighs. So what we're talking 100 is 100 billion photons per centimeter squared per second on this scale. Now this is early calibration days, so we haven't subtracted any backgrounds yet or anything like that. Dark noise is still in it, but it's very tiny, so we don't expect it to change too much. But we've got a lower spatial resolution. This is a 512 by 512 array, and we acquire an image that looks just like this every single hour. And with the narrow field imager, we've got a much tighter field of view, 3.6 degree full angle. You can see the difference. Earth is much larger here. And we've also got a higher resolution. So we don't bend the image on board before we telemeter it, or at least not as much. We send down the full 1024 by 1024 array. And because we're so sensitive, we can send that higher resolution image even faster. So we send 2 of those an hour. This little guy down here, that's the moon. Of course, this is only about 1.5 degrees away from Earth. So we're looking at it during new moon phase. It's just transited in front, and then it'll go off the edge of both fields of view and come back again. So the moon makes this kind of large oscillation. We see it about twice a month. Well, for sure we see it twice a month in the WFI field of view, and we frequently see it in the NFI field of view as well. Recently, we had a lunar transit. We're this most recent new moon phase. We're excited to be releasing that soon. Both of these cameras employ these identical. They're intensified. I'll talk about that process. How do we actually detect UV photons? But the cameras themselves were made by Utah State University Space Dynamics Lab, and we've got filter wheels. So let me talk a little bit more about that. So here's our optical path to cameras. So here's that wide field imager. Optical path is shown in yellow. Narrow field imager is shown in this cyan color. The filter wheels we employ, because if we didn't have a filter wheel there at all, we're able to essentially isolate and be sensitive to ultraviolet photons by virtue of the fact that our mirrors are coded. So you can see there's lots of mirror bounces. NFI bounces here, bounces there, and then heads to the detector here. WFI, it's a wide field imager, so it had to have a bit of a more compact folding. So we've actually got 4 mirror bounces. Bounce, bounce, goes through the filter wheel, another 2 bounces before it makes it into the detector. But the mirrors themselves are coded, so they have some capability for wavelength filtering in a way. They only allow ultraviolet photons to bounce at all. Different colors are going to not bounce the same way. And then we also have various component quantum efficiencies. I'll talk about that in a second. Essentially, what's happening down here in the detector, that's where the magic is, because what's coming in, everything is still ultraviolet so far. Filter wheel is here so that we can do further spectral filtering. So in addition to the open position, we also have 2 narrowband filters. These are really exclude anything that except Lyman-alpha. And we didn't know how bright the exosphere would be, so we launched two. We launched what we called narrowband. We weren't that creative with our names. Narrowband Lyman-alpha filter, and then extra narrowband. Essentially, it's got a lower throughput on peak, but it also suppresses more of the wings as well. But if the exosphere was much brighter than we expected it to be, we would be using the extra narrowband for routine imaging. But as it turns out, it's right where we thought it would be. And so we're currently using narrowband, and we just use extra narrowband for additional calibration of the signal. We've also got two more filters. So I mentioned that George Carruthers' camera himself couldn't exclude oxygen emission. We get some oxygen emission in it as well. So the Lyman-alpha line is at 1216 angstroms, and oxygen contamination is at 1304. It's not that far away. And so what we have here are these are crystal filters, calcium fluoride and strontium fluoride. When we put those in the optical path, they suppress Lyman-alpha and they let everything else through. They're long pass filters with a cutoff frequency such that the calcium fluoride lets in a little bit of 1304 and everything else. And strontium fluoride doesn't even let in 1304 along with everything else. Long wavelength, long pass transmission. And then of course we've got a blocked filter so that we can do dark calibration. So looking at the actual detector itself, how does light detection work? So here's our incident photons coming in. I showed you the optics and the filters already. Our target signal is going to be the solid line going through this diagram. And then we've got a background signal. So we've got Lyman-alpha emission also produced from resonant scattering of solar Lyman-alpha photons, but it's not an exospheric, gravitationally bound to Earth's atmosphere hydrogen atom. It's hydrogen atoms that populate interplanetary space, and we need to be able to detect and distinguish those two. So that's our in-band background, and then here's our out-of-band oxygen emission and whatnot background. Those are almost exclusively, they're 100% close to the Earth limb because those are much tighter gravitationally bound to Earth itself. All right, so once it makes it through the optics and the filters, it is impinging on a potassium bromide photocathode. And what this does is when an ultraviolet photon hits this cathode, it releases a very energetic photoelectron. This is the photoelectric effect that made Einstein so famous, earned him a Nobel Prize. That photoelectron, we call them events. Essentially, every photoelectron event is a detected photon. So there's a quantum efficiency associated with this. This is also highly wavelength dependent, so it's very sensitive to ultraviolet photons in particular. Lower energy photons don't have enough energy to liberate the electron, photoelectron. But they're so infrequent that there's too few of them to count. And so we need to gain amplify that signal. So what we do is we pass those photoelectrons into a microchannel plate. Inside, there's essentially a cascade. More and more secondary electrons get created. And then those electrons impinge on a phosphor screen. And every electron that hits the phosphor screen, again, with some quantum efficiency, is converted into a visible photon. It's green. And then our camera just takes pictures of the green photons. There is some other background that appears at this point, particle radiation, solar energetic particles. These are alpha particles, right? It's a proton, very energetic proton. They're moving so fast, they'll go right through the detector. They can impinge on the microchannel plate and excite their own cloud of secondary electrons. It gets counted just like a photon. Or they can impinge on the detector itself. That's where you get streaks. You've probably seen pictures of particle snow, so to speak. Then, of course, here's the dark signal. So we have an extremely comprehensive calibration. The fact that we're a standalone spacecraft, I'll show that in a second, means we can point wherever we want on the sky. So we do a lot of off-meter targeting of stellar sources so that we can get absolute sensitivity calibration. In fact, a byproduct of our mission will be one of the most comprehensive databases of ultraviolet stellar signals, calibrated stellar signals than currently exists. And then also this interplanetary hydrogen. We're going to be making maps of it because it's the background we need to subtract. We use it also for flat fielding because it's a pretty smooth distribution in interplanetary space. And then on Nadir, we use our filters to do that out of band characterization and subtraction. So it's extremely well calibrated Lyman-alpha data, and all of it is in an extremely compact spacecraft. So this is, unlike the huge flagship NASA missions, such as the IMAT mission that has, half a dozen sensors on it, we've got our one camera. Let's see what happened. Here we go. We have our one camera, the single primary science payload, and it's going to come back around again. There it is. There's our two field of view. And then this little guy poking right up over, kind of looking over the solar panels, that's that student photodiode, which is measuring the solar flux that's coming out. And the entire package is about the size of a commercial washing machine. So not too big. And we ordered the first piece of hardware in early 2021, and we finished testing the build and all of our ground components just about a year ago. So it's been a whirlwind, so to speak. You can see our solar panel here is fixed. And in fact, there's hardly any moving pieces at all. I'll show you. The only thing that moves on this camera is the doors to the cameras. So there's aperture doors. They needed to open. I'll show you a picture of what that looks like when they opened. But basically, here's our antennas on this side. Really simple design. Down inside this big cube, so to speak, the satellite bus, that's our propulsion tank. It's a big sphere filled with hydrazine. We squirt it out of jets in order to do our attitude control and to put us on track on the orbit of where we need to be on orbit. And we have now finished. We are now currently on orbit. We reached orbit. I might as well show you our milestones. So we launched it September 24th. Here is our rocket. You can see the different logos of the different ride shares. IMAP, of course, was that flagship primary mission that the reason the rocket existed at all. And then October 16th, here's a picture. Here's our door pop. This is not a real movie, obviously. This is an animation. But nonetheless, I have an exclamation point. It was the only moving part. If these hadn't opened, it would have killed our mission. We were all on bated breath watching this happen. This is a very simple mission. This was the hardest thing we had to do. Since then, we did cruise phase commissioning. It took about 4 months to get to orbit. And then finally, January 8th, we did our last propulsion maneuver that essentially made us turn at a right angle and get into this orbit around L1, that huge halo orbit you saw. And then every month or so, we do a little bit more propulsion to stay on orbit. And in fact, all of our maneuvers have gone so well and so closely according to plan that we are able to use all of that margin that we had for our propulsion, all those extra propulsion, just in case things didn't work out. We're going to be able to use it for science. So we have 12 years of propulsion available to run this mission before we slowly, essentially drift off into space around the sun. We began routine science operations, this is what known as science phase E of our primary 2-year mission on March 8th. We have 6 months until we deliver our first L2, it's called, data product. This is derived hydrogen density distributions, deriving it from those 2D images of the Lyman-alpha radiance that we're observing routinely now. After that, we'll do monthly data archiving until the end of our nominal science mission. And at that point, we'll be invited to submit a proposal for future, just like every other current NASA mission, extended phase opportunities. And we fully intend to be taking advantage of that. So here's one last video that the NASA visualization team made. I love this one because it gives the impression, just how big space is and how tiny our spacecraft is floating around out there. Once our mission is finally done with and it enters into orbit around the sun, it's just so interesting to me, more than interesting. It's so exciting to me that, barring an asteroid impact or something, it'll stay there for 1 billion years. I mean, that's just amazing. My students worked on that. So for those of you, I heard you mention education and outreach. I've got one slide just to let you know that we've got our own initiative. We've done a lot of work on this. We've got a Berkeley put together a really nice website. You can see the link here, but it's got everything from hands-on educational activities, teacher guides, tons of video products, all kinds of science career advice and science profiles and topical explainers and things like that. But it's also got activity demonstrators. So, what is UV light? You can see it with a black light, for example. UV, what is a magnetic field? Lots of things that educators can use, and lots of resources, essentially puzzles and things that we think would be fun for a younger audience, especially. And so with that, I'll stop. I'm happy to take any questions, and thanks so much for your attention and interest in seeing where Dr. George Carruthers' legacy has taken us all.
Question should be down here.
Okay, well, got one question in the room. Let me just see if there's anyone else online. Just 1 second.
Pretty sure there's at least one question online.
Okay, well, why don't we take the one in the room first? Go ahead, sir.
All right, my name is Paulos. I'm a member. First meeting, but I've been a member for about a year. You mentioned that there's hydrogen atoms involved. So that it's not a diatomic hydrogen molecule. I thought that the natural state of hydrogen was diatomic because it was at a lower energy state. But you're saying that out in the exosphere, they exist as a single atomic molecule?
That's
Please
correct.
explain.
That's correct. So there is a stage, they do go through H2. H2 is very common in the mesosphere in particular. So, around 80, 90, 100 kilometers, maybe even up to about 120. But it's pretty readily dissociated at those altitudes by UV photons in particular. And so once it's dissociated, it becomes a constituent hydrogen, 2 constituent hydrogen atoms. And at that point, they diffuse upwards through the rest of the atmosphere. But
So
you're right, it goes through an H2 stage for sure.
They don't recombine after a dissociation?
The density falls so quickly with increasing altitude. The concept of diffusive equilibrium, essentially every atom falls off with an exponential scale height according to its mass and according to the temperature of the atmosphere. And so hydrogen atoms being so light, they tend to exist the farther away. Heavier atoms are going to be held down more. But that's correct. They hardly, by the time you get to this altitude, we're talking at these altitudes, this is only 0.0001% of the mass in the atmosphere. I mean, it's incredibly tenuous at this point. We're above where the space shuttle orbits, well above where the space shuttle orbits, for example. But it's still gravitationally bound. So it's still technically Earth's, we call it the outermost layer, but it's hard to wrap your head around how tenuous it is. It looks transparent, for example, to an astronomer on the space station.
Thank you.
We got one more here.
Thank you for your presentation. That was wonderful.
My pleasure.
Particularly the instrumentation part of it. Do you know if, as part of the Artemis program, there are going to be potentially a Carruthers camera version 2?
For sure, nobody knows the answer to that yet. I have thought about it. We've thought about putting in a proposal. I've made it clear that I've got my hands full with this mission, but I definitely encourage others to do it. So I think it's possible that some proposals will go in, but everything right now is at the proposal stage. So I'm pretty confident no decisions have been made yet. I will say that I think it would be a coup for science, because the nice thing about Artemis is that it's got a different viewing geometry. So with our mission, I'll go back to the photographs. They look great and we've got great coverage around Earth, but we cannot see the night side, for example, right? There's a solid Earth void where our lines of sight will not cross that region no matter what our orbit is. There's always the other side of Earth. And the nice thing with Artemis is they would allow essentially stereoscopic sensing. In our case, we build up, we're going to be doing tomography with Earth as well, but it takes us weeks in order to get enough viewing geometry diversity to have something similar to what TWINS did with its multiple angle. You've got this different lines of sight crossing through the same volumetric region. It takes us a long time to get that. If we had another platform with a similar camera, we would be able to get that instantaneously. So I'm a big fan of having it on there. I think it would be great for science. I will say that I'm not personally championing that effort at this time. This one's keeping me plenty busy.
Understandable.
And George?
What happens when solar flares occur or mass ejections? What do you actually see from that?
Oh, that's a great question. We've seen one. I'm a little bit, we've got some I should have said this. We've got some very exciting things to show. It turned out that the very first time we did an extended nadir stare, it was our test, right? We've been taking engineering data. We've been in this mode the whole time during cruise phase. We've been commissioning the instrument and testing various things. And one of the things we tested in early January 19th and 20th to be specific. I'm sure that rings a bell because you guys already showed a picture of Aurora in Virginia on January 20th. That was the first time we ever stared continuously at nadir. And so we got to see that superstorm and how the exosphere responded. But what was interesting is during that storm, the sun is putting off solar flares, right? It was an extremely active event. And we were able to essentially observe that as well. So when the spacecraft upstream from Earth is engulfed in a SEP event, solar interject particle event, what happens is, let's go back here. Essentially, what you're doing is you're drastically, suddenly increasing the amount of particle radiation, both on the microchannel plate and on the detector. And so what that looks like to us is all of a sudden it gets brighter. Everything gets brighter all at once, every pixel, almost uniformly. We don't see as many particle streaks. And one of the reasons for that, I didn't mention this, but I guess it's relevant, is that, when we're staring for 30 minutes at a time, if a particle were to streak by and hit our detector, it would fill the electron well and would be done. And so by the time we integrate for 30 minutes, all those electron wells they're all full and we won't have any signal left over. And so what we do is we run the camera frame acquisition rate at 8 hertz. And so, we take 8 frames a second. And so if a particle impacts it in that 125 milliseconds, it might fill that one well. But by the time you stack it with the next frame and you do this 1,800 times to build up a 30-minute image, it's all a wash. And so energetic particles, they will show up as a brightening, uniform brightening. But in our images, if you see over here, these corners are outside the field of view. So our microchannel plate is bonded, connected. The output from the microchannel plate is connected to the phosphor via fiber optic. It's a fiber optic taper. Those electrons cannot go past the phosphor is connected to the detector via fiber optic taper. But the whole thing, everything is glued essentially together. Nothing can escape the field of view. So our dark corners are representative then of the energetic particle flux directly on the detector. And then when we see the whole scene get brighter and we watch the corners get a little bit brighter, that's how we distinguish something that's happening with photons versus something that's happening with particle radiation. But we definitely saw it during that event. We've seen it multiple times since then. That's a question.
Another question on that. Are you working with any other spacecraft that do collaborative observations, like say the Parker Solar Probe? Or are you doing anything yet?
We're just getting started on some of that. So IMAP itself, one of the goals of their mission is to measure the interplanetary hydrogen background. And we'll be making our own map because it's background signal that we need to subtract from our science data. But to the extent that that's their primary mission, now they'll be looking, they have many, many instruments beyond that one, but that's one of their goals. I fully expect that we'll be cross-calibrating and comparing, and filling in gaps, spatial gaps and so forth. Another mission, plenty of other missions are measuring products of the charge exchange reaction upstream of Earth. So for example, another effect of the charge exchange is an X-ray emission at the bow shock, at the magnetopause region, essentially upstream of the Earth or the sun. And so doing some comparisons of our data with theirs is going to be on the horizon. But, at this point, we are focused squarely on getting our images calibrated as quickly as possible. I don't know if you can see it here. These are not fully calibrated. We've still got voltage bias stripes from our column amplifier readout in these images. We're we're still kind of in the weeds when it comes to our own image calibration, but there certainly are opportunities for a lot of collaboration with both current and future NASA missions, especially the space weather missions. Parker Solar Probe in particular is probably not something. Yeah, it's okay. I saw that. But the Parker Solar Probe is probably all that not relevant. You know, we're not that much interested in exactly what's happening in the solar corona, except for the SEP events, you know, the local environment. And we have what we think is a pretty good energetic particle detector, essentially, looking at the background in our images.
Yeah.
I know we have it's one person online that has a question, so I was just trying to make sure I let him talk. That's what I was trying to do. I think Jay Birch, did you have something you wanted to ask?
John.
John. Hello.
You would need to enable, yes.
Okay.
His question was, would any
Yeah.
highly eccentric satellite be useful as sensors, essentially?
Any other?
Useful when you say sensor, like an in situ sensor, or a remote camera type, like one of these, for example.
I would imagine remote camera, but
Yeah. For sure, you know, if there was an imager on here, you know, that would be even better than having, you know, the little single pixels that physically rotate, mechanically scan. I think imager is always better. But in terms of the orbit itself, I think the best place to put an imager is as far away as possible. That way you get as much of the global exosphere. You know, 18-degree field of view is about as big as we could make it. And in order to, and even then we're not sure we're seeing the whole exosphere. If you go back to this wide field imager here, this goes out to about 30, 40, 35 to 40 Earth radii. It depends exactly on where we are in our orbit. The radial distance from Earth changes a little bit. As I mentioned, the moon's at 60. But if the exosphere extends all the way to the moon, then, you know, we don't have any background even within our field of view. So the idea, I think, is to get as far away as possible. That's what allows you to make images something like this. You know, so we're at 240 Earth radii. This one was 10 times farther away. We don't want to be that far away because that's not gravitationally stable. But anything Earth orbiting is a bit tricky to infer in terms of global structure. You know, interpret because you're just not sampling it as easily as you could if you were outside the entire exosphere looking back.
Okay, got one more question here.
Yes, Carlos again. You mentioned that the only moving part in the satellite was the aperture door. Would not the filter wheel have some mechanism to select the optical filter?
That's true. That's true. I guess you're right. That's very true. When I say moving part, what I was referring to is a certain kind of moving part. NASA categorizes as a high risk, right? So this was mission critical moving part. If this moving part didn't move, but a lot of NASA, I mentioned that to distinguish it from NASA missions. A lot of them have deployable booms, for example, or they have solar panels that unfold. You know, ours had none of that. Ours was so simple. The only mission critical moving part was those doors popping open. But you're absolutely right. We moved that filter wheel multiple times per hour. And, you know, if it were to get stuck in the blocked position, we'd be in big trouble. We did test that thoroughly. And so far we haven't had any issues. But that's a good point. That's definitely a moving part.
thank you.
Okay, nothing else here. And anybody else online?
It looks like there's one, I think David has a question or his hand's up.
Well, I just want to say I think George would have been very, very proud of all of this. He was a quiet but wonderful genius. Yeah.
That means a lot to me, David. I really appreciate that. I really do.
I really appreciate your presentation. In many ways, it keeps George's goals alive. And even though of course, the underlying issues at the George's time was pretty much ionospheric physics and solar terrestrial relations. But I assume you have in the same goals, the same scientific goals.
It's correct. Absolutely. You know, I mean, if anything, the exosphere just in the past decade has become more significant for those same goals. So, you know, it's one thing to have the interest, as you say, in solar terrestrial physics, and in practical terms, the practical reason for doing that is, of course, that space weather causes all kinds of havoc for technological assets and systems. But what we've learned just in the last 10 years is what an incredibly critical role the exosphere plays in that response. And that would have never been appreciated. Exosphere was, oh, sure, it's the path for H escape. Oh, but it's so slow. You know, it's nothing to worry about. We'll make a few measurements of some globally average escape flux, and then plug in a spherically symmetric, time invariant exosphere into all our models, and we'll be fine. Just in the last 10, 15 years, that has been shown to be radically untrue. And that, you know, not getting the density right, and especially not getting its time variability right, changes recovery timescales by days, you know. And so it's true that was his goal as well. But I think what's changed in that time is the recognition of how significant the exosphere is, and he was really the pioneer of exospheric science, to be sure, and therefore his what he started has only grown in importance since then.
I really think he would have been very proud of your work. Can I put in a plug for the book?
Absolutely, please do.
Okay. I wrote a biography of George. It came out in May 2025, and you can find it. It's open access online, or you could actually buy a copy if you really want to. And you can find it by simply putting in Google my name, Dvorkin, Devorkin, and Carruthers, Carruthers, and the MIT link comes right up. So thanks so much, Laura.
Thank you so much. I'm glad you could be here.
Yeah, well, I finally made it, getting through my computer.
Okay, well, thank you very much. And of course, we had a presentation from on the same subject last year. We appreciated, David, for you chiming in on this important subject. Anything else from anyone else? Am I missing anyone else online?
I see a hand up from Candace.
Oh, yeah, I'm sorry. Yeah, go ahead, Candace.
Hi, sorry, real quick, I got in late. Is there a link to like your website? I'm at your university site, but
you know what? Okay, so that's you've put me on the spot. Illinois I do not yet have, even on my homepage, can you believe it, a link. NASA has a pretty thorough link. We have a link here, Space Weather, SSL Berkeley, that talks a lot about the Carruthers mission. But it has been on my list of things to do. And I'll tell you, once we got first light, it has been a whirlwind. And I have not had time to make it active.
oh, that's okay.
Yeah,
I'll go through NASA and Berkeley. That'll work.
Right. Yeah, you can find more details there. There's plenty online.
Thank you very much.
Yeah, I have not made it easy for people myself.
Laura, when you get to it, let us know and we'll let the members know here.
Sure. Yeah. I'll keep you posted for sure. And like I said, we're planning so that storm, the 1920th storm, we are it's on an embargo essentially from NASA at this point. But when we publish it, we fully expect to make the cover of Science, and I'll be sure to keep you posted on that, because it was extremely exciting what we observed. Very dramatic.
Great. Well, thank you very much for your time. Thank you very much for the presentation. It's been very interesting. Hope you come visit with us in person sometime when you get out of Illinois and down this way.
Absolutely, my pleasure.
Come to dinner or come out and observe with us. But this is very interesting stuff. You know, we have launches every other day going on right up in all of that area, and people want to know about the space weather a whole lot more than they ever did before. So this is really important stuff, and we really appreciate your time, and thank you very much for.
My pleasure. Thanks everybody for joining. I really appreciate the attention and interest.
Great. Well, thank you. So if we don't have anything else further, I think that's the bottom. We're actually running a tad late. We had that technical issue, but we appreciate it. And thanks everyone else for joining us, and we'll see you out there observing.